Imagine waking up tomorrow morning to a sky that slowly warps and a sun drifting out of its alignment. There is no sudden explosion, no wailing warning sirens, only an invisible rogue black hole silently slipping into our solar system. Gravity begins to pull at Earth's crust, warping the fabric of space and causing time itself to stretch. Tonight, turn down the lights, relax, and journey into deep physics to explore what happens when an unseen titan collides with our world, and how the universe responds when its fundamental laws break down. Welcome back to Dozing Doctor, your sanctuary at the edge of the known cosmos. Here, we blend deep physics, astronomical mysteries, and theoretical science into immersive explorations designed to quiet an overactive mind and guide you into deep relaxation. Tonight, we step into a scenario that defies human imagination. What if an unseen titan, a rogue black hole, silently enters our solar system tomorrow? What happens to space, gravity, and the flow of time when Earth meets the ultimate cosmic shadow? Dim your lights, put on your headphones, and let your mind drift past the waking world as we explore the quietest apocalypse in the universe. The universe is often depicted as a grand architectural clockwork, stars anchored to galaxies, planets locked in predictable orbits around stellar fires, and galaxies spinning in structured cosmic webs. We measure time by these celestial rhythms: the spin of our planet, the arc of our orbit around the sun, and the calm stability of the Milky Way's spiral arms. Yet, hidden beneath this illusion of cosmic order lies a vast, pitch-black ocean driven by violent births and chaotic mechanics. Among the billions of stars and quiet worlds drifting through the dark, there exist phantom entities that acknowledge no solar system, obey no galactic anchor, and cast no light. These are rogue black holes. Unlike the supermassive black hole at the center of our galaxy, Sagittarius A, which sits like an immense gravitational anchor keeping millions of stars in a measured ballet, rogue black holes are cosmic nomads. They wander through the interstellar void between stars, moving across light years at staggering speeds. Unbound by gravity to any home star system, they drift in total darkness, invisible to traditional telescopes and utterly silent. To understand what it means if one were to approach our solar system tomorrow, we must first unspool the fundamental nature of these cosmic wanderers, how they are forged in catastrophic stellar deaths, why they were cast out into the dark, and why they remain among the most elusive and profound objects in theoretical physics. To grasp the nature of a rogue black hole, one must understand that a black hole is not a hollow drain or a literal hole in space. It is a mass so concentrated, squeezed into a region so tiny, that space itself collapses under its sheer density. When a massive star, at least 20 times the mass of our Sun, exhausts the nuclear fuel in its core, it can no longer sustain the outward pressure of fusion. For millions of years, thermal pressure pushed outward against gravity, keeping the star stable. But when the nuclear fire dies, gravity wins instantly, and absolute force collapses the core inward in fractions of a second. The outer layers detonate in a supernova, one of the most energetic explosions in the cosmos. Meanwhile, the inner core collapses down past atomic structure, past neutron degeneracy pressure, down to an infinitesimal point of infinite density known as a singularity. Around this singularity forms the event horizon, the theoretical boundary where the escape velocity of space exceeds the speed of light. Nothing that crosses this boundary, no light, no radio signal, no physical matter, can ever escape. The black hole emits no photons of its own, making it completely invisible against the black backdrop of deep space. Most black holes remain near the stellar nurseries where their parent stars were born, orbiting peacefully within the gravitational potential of their host galaxy. How, then, does a black hole become a rogue? The primary mechanism is supernova recoil. When a massive star dies, the supernova explosion is rarely perfectly symmetrical. If the star's core collapses with even a slight asymmetry in its mass distribution or neutrino emission, The resulting explosion acts like a rocket thruster. The expanding shell of gas detonates more violently in one direction, kicking the newly formed black hole in the opposite direction. This process can fling a stellar mass black hole out of its natal star cluster at velocities exceeding hundreds of kilometers per second. It is launched into interstellar space, severed forever from the star system that birthed it. Another primary path is dynamical ejection in star clusters. In dense environments like globular clusters, swarms of hundreds of thousands of stars packed tightly together, black holes frequently interact with other massive bodies. When two black holes form a binary pair and encounter a third massive star, complex gravitational mechanics come into play. In these three-body interactions, kinetic energy is exchanged chaotically. Frequently, the lightest body or one of the black holes absorbs a massive burst of kinetic energy and is violently slingshot out of the cluster, sending it wandering through the galactic disk alone. On an even grander scale, when two galaxies collide, their central supermassive black holes gradually sink toward the center of the merged galaxy, forming a supermassive binary pair. If a third galaxy enters the collision before the first two black holes merge, a chaotic three-body interaction on a galactic scale ensues. The gravitational forces can eject an entire supermassive black hole, containing millions or billions of solar masses, out of its host galaxy entirely, leaving it to drift through the intergalactic void forever. Because a rogue black hole produces no light, detecting one drifting through interstellar space is one of the greatest challenges in modern astronomy. It does not glow like a star, nor does it reflect light like a planet. Unless it actively feeds on a nearby cloud of interstellar gas, heating the gas to millions of degrees and releasing X-rays, it is entirely black. However, gravity cannot be hidden. According to Albert Einstein's theory of general relativity, mass bends the fabric of spacetime. When a massive object passes directly between a distant star and Earth, its gravity acts like a cosmic magnifying glass, bending and focusing the light from the background star toward us. This phenomenon is known as gravitational microlensing. To an observer on Earth, the background star does not suddenly look like a black hole. Instead, it temporarily brightens over weeks or months as the rogue black hole passes in front of it, then dims back to its normal state as the black hole drifts away. By carefully analyzing the duration and shape of this brightness curve, astrophysicists can calculate the mass of the invisible lens, confirming the presence of a wandering black hole in the dark. Astronomers estimate that there could be upwards of 100 million stellar mass black holes wandering quietly through the Milky Way galaxy. The vast majority of them drift through the vast gaps between solar systems, light years away from any planet or star. The probability of one entering our immediate solar system is infinitesimally small on human timescales. But in theoretical physics and cosmic thought experiments, we must ask, what if the geometry of space aligns against us? What if one of these silent wanderers has been traveling toward our sun for millions of years and reaches our doorstep tomorrow? Imagine a rogue black hole with a mass roughly 10 times that of our sun, but with an event horizon spanning only about 60 kilometers in diameter, roughly the size of a medium city. It travels at 400 kilometers per second. It carries no lights, gives off no sound, and leaves no visible trail. Long before it touches a single planet, its arrival is announced not by a flash of light, but by a subtle, unsettling disruption in the gravitational balance of our outer solar system. As it crosses the distant boundary of the Oort cloud, trillions of icy comets orbiting in the frozen fringes of our system, it pulls at the fabric of space itself. Comets are tugged out of their ancient orbits, sent cascading inward toward the inner planets or hurled out into deep space. The cosmic clockwork begins to lose its tempo. The quiet sky begins to warp. The unseen Titan has entered our realm, setting into motion an irreversible sequence of orbital instability, gravitational lensing, and extreme spacetime distortion that will reshape Earth's destiny forever. Chapter 2. 24 Hours Out. Gravitational instability and orbital shifts for 4.5 billion years. The solar system has maintained a delicately balanced cosmic dance. Earth loops gracefully around the Sun at an average distance of 149.6 million kilometers, moving at a precise orbital velocity of roughly 30 kilometers per second. This balance is governed by the Sun's gravitational mass, which dictates the trajectories of every planet, asteroid, moon, and comet in our planetary neighborhood. It is a predictable system, so constant that humanity has built its entire calendar, history, and perception of time around these exact celestial mechanics. However, when a rogue black hole traveling at 400 kilometers per second crosses the invisible boundary of our solar system, this ancient equilibrium vanishes. A stellar mass black hole weighing 10 times the mass of our Sun does not need to physically strike Earth to end our world. Its sheer gravitational footprint is a massive anomaly. Long before its event horizon reaches the inner planets, its immense gravitational field begins pulling at every object in the solar system, rewriting the laws of celestial movement that have kept our planet stable for billions of years. As the rogue entity approaches the outer rim, passing beyond the orbit of Neptune, it enters a region inhabited by millions of frozen worlds, the Kuiper Belt. Normally, these icy bodies trace quiet, slow circles around the distant Sun. But as the black hole sweeps through, its gravitational pull completely overrides the gentle hold of the Sun. Trillions of tons of ice, rock, and dwarf planet fragments are yanked out of their ancient paths. Some are hurled outward into the interstellar void, lost forever. Millions of others are deflected inward, creating a cascade of chaotic trajectories that rain down toward the inner solar system. In classical orbital mechanics, a planet's path around a central star is described by Kepler's laws of planetary motion, governed by Isaac Newton's law of universal gravitation. $F equals G backslash frac M 1 M2 R2 here. The force of gravity depends on the two masses and drops off with the square of the distance between them. For billions of years, the Sun's mass dominated this equation for Earth. But with a 10 solar mass black hole entering the system, the single-body dominance disappears. The solar system transforms overnight from a stable system into an unpredictable, chaotic end-body problem. 24 hours before the black hole reaches its closest approach to Earth, the sky above us remains quiet to the naked eye. The Sun rises on schedule in the east. The atmosphere is clear, and the afternoon breeze carries no immediate hint of catastrophe. Because a black hole emits no light, there is no glowing fireball across the horizon, no fiery comet tail, and no dark sphere blocking out the Sun. Yet, at a microscopic and atomic level, the fundamental fabric of Earth's environment is already destabilizing. Scientific instruments around the world are the first to sound the alarm. Atomic clocks, which measure time by observing the microwave signals emitted by electrons changing energy levels in cesium atoms, begin to drift out of synchronization. Under general relativity, gravitational potential alters the local flow of time. As the intense gravitational wave front of the approaching black hole rolls across the planet, time itself stretches by fractions of a nanosecond, causing global satellite navigation networks and high-frequency communication systems to glitch. Simultaneously, supersensitive laser interferometers built to detect gravitational waves register an unprecedented, low-frequency hum vibrating through spacetime. Space is not merely empty distance. It is a physical fabric. The movement of an object so dense warping space around it creates ripples that stretch and compress the Earth by distances smaller than an atomic nucleus, vibrating through the planet's core. As the 24-hour mark ticks down, the gravitational pull of the approaching wanderer begins to interfere directly with Earth's orbit around the Sun. Earth does not instantly plunge toward the black hole, nor does it immediately fly out of the solar system. Instead, its smooth elliptical orbit begins to stretch and warp. This orbital shift alters Earth's orbital speed and distance from the Sun. Even a minor deviation of a few percent in our distance from the Sun triggers dramatic climate and atmospheric shifts. As the distance fluctuates, the atmospheric pressure gradient changes. Oceans begin to bulge uncharacteristically. On Earth, we are familiar with tides caused by the gravitational interaction between the Earth, Moon, and Sun. Tidal forces occur because the pull of gravity is stronger on the side of a body closest to the attractor than on the far side. The differential gravitational force, the tidal force, stretches the planet along the line of sight toward the massive object. The differential force acting on Earth can be expressed mathematically as $F text tidal \approx \frac2 GMMRR $3 in this relationship. M$ is the mass of the black hole, M$ is Earth's mass, R$ is Earth's radius, and R$ is the distance separating Earth from the black hole. Notice that while gravitational force decreases with the square of distance, R2, tidal force decreases with the cube of distance, R3. This means that as the rogue black hole closes the distance during these final 24 hours, the stretching forces experienced by Earth do not increase linearly. They surge exponentially. 12 hours before impact, these rising tidal forces begin to impact Earth's liquid oceans and solid crust. Water is pulled away from coastlines in some regions, building into massive, slow-moving oceanic bulges, while receding completely in others. Deep within the Earth, the molten iron outer core experiences gravitational tugs that conflict with the planet's natural rotational dynamics. This internal friction generates colossal stress along tectonic fault lines. Earthquakes ripple through deep subsurface rock layers, and dormant volcanoes show sudden surges in magma pressure as the planet's crust is squeezed and distorted like a rubber sphere. In the night sky, subtle optical anomalies begin to reveal the phantom's exact location. While the black hole itself remains entirely dark, its extreme gravitational field warps the paths of light passing near it. Distant stars positioned directly behind the approaching black hole appear to move, duplicate, and stretch into glowing arcs of light, a phenomenon known as gravitational lensing. The familiar constellations of the night sky distort into shimmering rings and mirrored streaks, as if viewed through the base of a curved glass bottle. As the final hours of the 24-hour mark approach, Earth's path is no longer a stable orbit around the Sun. Trapped between the immense gravitational pull of our home star and the overwhelming force of the incoming wanderer, Earth is drawn into an unstable, hyperbolic trajectory. The celestial mechanics that nurtured life for billions of years have dissolved into pure kinetic chaos. The sky remains tranquil to the sleeping world, yet the stage is set for the ultimate cosmic encounter. In the next chapter, we look closer at this optical warping as light bends to its absolute limit, transforming the night sky into a frozen display of distorted space and time. For all of human history, the night sky has served as an unwavering anchor. Stars drift predictably across the dark, their light traveling across quadrillions of kilometers in straight lines to reach our eyes. When you look up at constellations like Orion, Ursa Major, or the faint band of the Milky Way, you are seeing light that moved unhindered through the cosmic void for decades, centuries, or millennia. Space, to the human mind, feels like an empty, rigid stage through which light travels without deflection. Yet light does not travel through a static backdrop. It moves across the physical fabric of spacetime, and that fabric can be bent, stretched, and folded by mass. When a rogue black hole moves through the solar system, it acts as the ultimate cosmic lens. Long before its physical gravitational pull tears at Earth's crust or disturbs our atmosphere, its presence transforms the vault of heaven into a surreal, optical illusion. The sky itself begins to warp, bend, and freeze. The fabric of warped space. To understand why the sky distorts around an invisible black hole, one must abandon the idea that light moves only in rigid straight lines. Under the principles of general relativity, A massive object does not pull on light using a physical force. Instead, the mass of the black hole warps the very geometry of space around it. Imagine a heavy iron sphere resting on a stretched sheet of flexible rubber. The sheet dips downward, creating a deep funnel around the sphere. If you roll a small marble straight across the sheet, its path will curve around the dip, deviating from a straight line. Light moving past a black hole behaves in the exact same way. Space itself is curved. And so the straightest possible path for a photon, a single particle of light, becomes a curve. The path that light follows through curved space is known as a geodesic. When a rogue black hole weighing 10 times the mass of our Sun enters our neighborhood, it creates a gravitational pit in spacetime so deep that light passing anywhere near it is severely bent. The closer a light ray passes to the central singularity, the sharper its curve becomes. Light rays that would have missed Earth by millions of kilometers are bent around the black hole and redirected straight into our sky. Conversely, light rays from stars positioned directly behind the black hole are split, stretched, and magnified, creating optical phenomena that human eyes have never witnessed up close. The birth of the shadow and the photon sphere. Because a black hole radiates no photons of its own, it cannot be seen directly. But as it bends the light of the universe around it, it casts a distinct silhouette against the background of space. This dark void is bounded by a luminous boundary known as the photon sphere. The photon sphere is a region outside the event horizon where gravity is so strong that photons are forced to orbit the black hole in unstable circles, much like planets orbit a star. At this precise distance, 1.5 times the radius of the event horizon, a photon can loop around the back of the black hole, circle it multiple times, and then break free toward an observer on Earth. If an astronaut were positioned precisely at the photon sphere, looking forward with a flashlight, the light from that flashlight would loop all the way around the black hole and strike the back of the astronaut's own helmet. They would literally see the back of their own head floating in front of them in the cosmic dark. From Earth's perspective, as the rogue black hole approaches, the photon sphere creates a razor-thin, brilliant ring of concentrated starlight surrounding an orb of total, impenetrable darkness. This dark center is not the event horizon itself, but the black hole's shadow, an optical silhouette created because any light that crossed closer than the photon sphere was permanently captured, swallowed into the abyss, and forbidden from reaching our eyes. The formation of Einstein rings. As the hours tick down and the rogue black hole aligns between Earth and distant stars, astronomers and stargazers observe one of the most remarkable predictions of theoretical physics, the formation of Einstein rings. When a background star aligns perfectly behind the center of the approaching black hole, the light from that single star cannot travel straight through. Instead, the light is bent symmetrically around every edge of the black hole's gravitational field. The single point of light from the distant star is smeared into a perfect, glowing circle of light encircling the central shadow. If the alignment is slightly off-center, the single background star does not form a complete ring. Instead, its light is split into two distinct, crescent-shaped arcs on opposite sides of the black hole's shadow. These twin images appear mirrored and magnified. As the black hole continues its silent sweep across the sky, these twin arcs slide along the perimeter of the shadow, stretching into long, fiery filaments before snapping back together into a single point as the alignment breaks. Multiply this phenomenon by millions of background stars. As the black hole glides past the plane of the Milky Way, the thousands of stars that normally form the dense galactic core begin to dance, warp, and multiply. The Milky Way no longer appears as a continuous band of faint white light. It splits into swirling, mirrored arcs, twisting into a cosmic spiral centered on an invisible point of absolute blackness. Constellations in melting glass. To the naked eye on Earth, the night sky undergoes a slow, ghostly transformation. There are no sudden flashes of light, no deafening sounds, and no violent fires in the atmosphere. The transformation is entirely silent, lending it an eerie, atmospheric beauty. Imagine looking up at familiar constellations like Orion. As the black hole glides across that sector of the sky, Betelgeuse and Rigel are no longer where they ought to be. The straight lines of the constellation bend like drawings on a stretched rubber sheet. Stars appear to push away from the approaching dark shadow, magnifying in brightness as their light is focused toward Earth by gravitational lensing. A star that was once barely visible to the naked eye suddenly blazes with immense intensity because the black hole's gravity acts like a lens thousands of kilometers wide, gathering photons that would have scattered into deep space and focusing them directly onto our planet. The star brightens, distorts into a double image, wraps around the black hole's dark halo, and then abruptly vanishes as it passes directly behind the event horizon. The sky appears as though it is being viewed through the bottom of a heavy crystal wine glass. Space itself looks fluid, rippling as the massive wanderer slides across our line of sight. The daytime horizon and the warped sun. The optical illusions are not limited to the night sky. If the path of the rogue black hole brings it into alignment near our sun during the daylight sky presents a sight that defies all human experience. Sunlight traveling toward Earth is caught in the black hole's gravitational funnel. As the black hole passes near the line of sight between Earth and the sun, sunlight is bent around the invisible sphere. Observers on Earth see a secondary, distorted crescent of sunlight appearing on the opposite side of the sky from where the sun actually sits. The atmosphere remains blue, scattered by nitrogen and oxygen molecules, but the source of that light appears fractured. A glowing ring of solar light forms around an invisible circular void in the daylight sky. Shadows cast on the ground lose their sharp edges, doubling and curving in response to the split rays of bent sunlight. The sun itself appears elongated, drawn into a luminous crescent that wraps around the edge of an unseen cosmic shadow. Time dilation and the gravitational redshift of light. Light bending is not merely a change in direction. It is also a change in energy and time. General relativity reveals that gravity alters the flow of time itself. Clocks tick slower in deeper gravitational fields. Because light is an electromagnetic wave whose frequency corresponds to time, light escaping from a deep gravitational region suffers a phenomenon known as gravitational redshift. As light passes close to the rogue black hole's photon sphere before curving toward Earth, it must climb out of a massive gravitational well. To do so, the photons lose energy. Losing energy does not slow light down. Light always travels at the absolute speed of light in a vacuum, but it lowers the light's frequency and stretches its wavelength. Visible starlight that enters the black hole's immediate vicinity is stretched into longer, redder wavelengths as it escapes toward our eyes. A crisp, blue-white star passing near the perimeter of the shadow transforms before our eyes. Its color shifts to amber, then to a deep, blood red, and finally fades into invisible infrared light as its frequency is stretched to infinity. Conversely, light that is caught in the path of the black hole and compressed by its extreme forward motion experiences a gravitational blue shift, shifting upward into blinding ultraviolet and X-ray spectrums. The perimeter of the black hole becomes a spectrum of shifted colors, glowing with infrared rings on one side and violet halos on the other. The concept of the frozen sky. Perhaps the most profound optical effect of gravitational lensing is the illusion of frozen time. Because light can take multiple paths around a black hole, some paths moving straight, others looping around the back of the object 1, 2, or 3 times before escaping, the light arriving at Earth from a single event is split across time. If a flare erupts on a distant star behind the black hole, we do not see it once. We see the direct light arrive first. Moments later, we see a second image of the flare arrive, created by light that looped around the left side of the black hole. Hours later, A third image of the same flare arrives, carried by photons that looped entirely around the back of the black hole before reaching us. The black hole acts as an optical time capsule, replaying past light in nested concentric rings around its shadow. The sky becomes a hall of mirrors where past and present exist simultaneously in shimmering circular layers. To an observer watching this phenomenon unfold from a quiet place on Earth, the universe seems to slow down. The chaotic rush of existence feels suspended within these endless loops of light. Space is no longer a void. It is a sculpted mirror, reflecting the history of the stars around an immovable shadow. The twilight of vision. As the 24-hour mark reaches its final stages and the rogue black hole moves ever closer to Earth's position, the gravitational lensing reaches its absolute mathematical limit. The black hole's shadow expands to cover huge segments of the sky. The background universe is pushed to the outer edges of our field of view. Looking up, one no longer sees a clear sky with a black hole in it. Instead, one sees an immense, swirling sphere of darkness surrounded by a compressed, hyperbright ring that contains the distorted image of the entire universe squeezed into a single ribbon of light. Every star, every planet, and the sun itself are smeared together inside this radiant halo, encircling the absolute quiet of the central void. Space has closed in on itself. The sky has frozen into a singular, glowing horizon surrounding the darkness of the ultimate wanderer. In the next chapter, we step beyond the visual warping of light and delve into the deep physics of time itself. How the passage of seconds, minutes, and hours slows down to a crawl as we approach the extreme gravitational field of the event horizon. To human minds, time feels like an absolute, universal constant. We picture an invisible clock ticking at the exact same pace across every corner of the cosmos, from the gentle tick of a wristwatch on Earth to the distant, swirling core of a far-off galaxy. We organize our lives around the assumption that a second here is a second everywhere. Yet, one of the most astonishing revelations of modern physics is that absolute time is an illusion. Time is not a rigid backdrop. It is a dynamic, elastic fabric woven directly into space to form spacetime. And like a flexible sheet, spacetime can be stretched, compressed, and warped by velocity and mass. When a rogue black hole enters our solar system, it does not merely exert a physical pull on rocky continents and deep oceans. It plunges our region of space into a profound gravitational well, where the flow of time itself begins to break down. The elasticity of spacetime. Before Albert Einstein introduced his theory of general relativity, Isaac Newton's view of the universe dominated science. Newton treated space as a fixed three-dimensional stage and time as an independent stream flowing smoothly at a uniform rate. But Einstein realized that space and time cannot be separated. They exist as a unified four-dimensional continuum, spacetime. Mass tells spacetime how to curve, and the curvature of spacetime tells mass how to move. When you stand on Earth, your feet are closer to the planet's center of mass than your head. As a result, gravity pulls slightly harder on your feet than on your head. Because gravity is simply the curvature of spacetime, time actually passes slightly slower at your feet than at your head. Atomic clocks placed on top of high mountains tick fractionally faster than atomic clocks placed at sea level. On Earth, this difference is measured in billionths of a second, too minute for human senses to perceive, but vital for technology like GPS satellites, which must constantly adjust their internal clocks to match the faster flow of time in orbit. Now, replace Earth's gentle gravitational dip with the steep, crushing abyss of a 10 solar mass rogue black hole. As this phantom wanderer sweeps closer to our planet, the gradient of time across our solar system changes dramatically. The tale of two clocks. To understand what happens as Earth enters this immense gravitational field, imagine two identical, ultra-precise atomic clocks. Clock A is placed on a deep space probe parked safely billions of kilometers away, far beyond the influence of the black hole. Clock B is situated on Earth as the rogue black hole approaches. From the perspective of an observer standing on Earth next to Clock B, nothing feels unusual locally. Your heart beats at its normal rate of 70 beats per minute. A second feels like a second. Your breath flows in and out with familiar rhythm. This is known in physics as proper time, the time measured by a clock that is stationary relative to the observer. In your own frame of reference, your clock always ticks at 1 second per second. However, if you look out through a telescope at clock floating far away in deep space, you notice an unsettling discrepancy. Clock A is ticking rapidly. The seconds on the deep space probe are flying by faster than yours. Conversely, if an astronaut sitting next to Clock A looks down at Earth through a powerful telescope, they see a world trapped in slow motion. They watch Earth's rotation drag to a crawl. They see clouds drifting lazily across the atmosphere, waves freezing mid-crest on ocean surfaces, and human movements stretching out into impossibly long, deliberate gestures. To the outside observer, Earth is sinking into a deep temporal swamp. The stronger the black hole's gravitational pull becomes around Earth, the slower Earth's time moves relative to the rest of the universe. Gravitational redshift as temporal stretching. This temporal stretching is not just a theoretical concept, it manifests physically through light. Light itself is a clock. A beam of light consists of electromagnetic waves oscillating at precise frequencies. When light leaves an atom on Earth and travels outward toward deep space, it must climb out of the black hole's steep gravitational well. To climb against that extreme spacetime curvature, the light beam must give up energy. Because light always travels at a constant speed in a vacuum, it cannot slow down to lose energy. Instead, it loses energy by stretching its waves. The frequency of the light drops and its wavelength lengthens. The light shifts toward the red end of the spectrum, a process called gravitational redshift. Redshift is the visual signature of time slowing down. If you broadcast a green laser light signal from Earth into deep space every exact second, the observer far away does not receive the pulses every second. To them, the pulses arrive seconds apart, then minutes apart, then hours apart. The green light of the laser stretches into deep crimson, then into invisible infrared radiation, and finally into long, faint radio waves. The light is literally carrying the slowed rhythm of Earth's time out into the cold cosmos. The event horizon and the frozen moment. As the black hole moves even closer, and the gravitational field approaches its absolute peak near the event horizon, time dilation reaches an infinite limit. In physics, the event horizon represents the ultimate point of no return. It is the boundary where the escape velocity of space equals the speed of light. But from a relativistic standpoint, it is also a temporal boundary, a place where coordinate time, as measured by an outside observer, stops completely. If a space probe were dropped directly toward the black hole's event horizon, two completely different realities would unfold simultaneously. To the observer watching from a safe distance, the probe never actually appears to cross the event horizon. As the probe falls deeper into the gravity well, its light becomes increasingly redshifted and dim. The probe appears to move slower and slower as it nears the dark boundary. Just as it reaches the exact edge of the horizon, the probe seems to freeze in space. Its image fades into a faint red ghost and slowly disappears into darkness. From the outside universe's perspective, it would take an infinite amount of time for the probe to cross that line. Yet to an astronaut riding inside that falling probe, the experience is entirely different. They feel no sudden freeze in time. Their watch continues to tick normally. They fall straight through the event horizon in a finite, fleeting moment, crossing from the external universe into the interior of the black hole without ever noticing a barrier in time itself. The event horizon acts as a one-way mirror in time. Information, light, and matter can pass inward, but the time elapsed on the inside is forever disconnected from the cosmic clock of the outside world. A quiet cosmic pause. In the quiet, atmospheric realm of theoretical physics, time dilation offers a fascinating perspective on existence. It reveals that time is not a master tyrant holding the universe to a single, relentless rhythm. Time is flexible, gentle, and deeply connected to place and presence. As Earth drifts through the extreme gravitational ripples of an approaching wanderer, the universe outside our world may speed ahead, living out millions of years in cosmic history. But here, within the deep curve of space, seconds stretch out into vast, peaceful expanses. The ticking of the cosmic clock softens, allowing the universe to slow down, pause, and breathe. In the next chapter, we shift from the quiet elasticity of space and time to the physical forces acting upon our world, examining how these intense gravitational gradients begin to dismantle Earth's protective atmosphere and reshape its surface. For hundreds of millions of years, life on Earth has flourished beneath a thin, glowing shell of gas. To an observer standing on the surface, the sky feels infinite, an endless ocean of azure blue by day and a dark, starlit vault by night. Yet, when viewed from the cold isolation of space, our atmosphere is revealed for what it truly is: an impossibly delicate skin, no thicker relative to the planet than the fine layer of condensation on a damp glass. This thin veil, composed of nitrogen, oxygen, argon, and trace gases, is Earth's primary life support system. It traps the warmth of the sun, distributes heat across latitudes, absorbs deadly solar ultraviolet radiation, and shields the surface from a relentless barrage of space debris. Above all, it exerts a gentle, continuous barometric pressure that allows liquid water to flow, oceans to remain stable, and living cells to maintain their structural integrity. However, the stability of this shield relies on a delicate balance between Earth's surface gravity and the thermal motion of gas molecules drifting in the vacuum of space. When a 10 solar mass rogue black hole enters the inner solar system, this ancient equilibrium is broken. Long before the black hole's event, horizon comes close enough to tear apart solid rock or rip continents from the crust. Its immense gravitational field begins to interact with the fluid, flexible outer layers of Earth's atmosphere, the invisible boundary of the upper air. To understand how an approaching black hole strips a planet's air, one must first look at how Earth holds onto its sky. Earth's atmosphere does not end at a sharp, solid ceiling. Instead, it grows progressively thinner with altitude, fatting smoothly into the near-total vacuum of space through several distinct layers. The troposphere, the dense, weather-filled realm extending from the surface up to about 12 kilometers, containing roughly 80% of the atmosphere's total mass. The stratosphere and mesosphere, rising tens of kilometers higher, housing the ozone layer that filters harsh, energetic radiation. The thermosphere and exosphere, the distant, glowing upper fringes stretching hundreds of kilometers into space, where sparse gas molecules orbit Earth like microscopic satellites. At these extreme altitudes, gas molecules move at high speeds, energized by solar radiation. Normally, Earth's gravity is strong enough to keep all but the absolute lightest elements, such as trace amounts of hydrogen and helium, anchored to the planet. The heavy molecules, like nitrogen and oxygen, remain firmly trapped near the surface. As the rogue black hole glides toward Earth, it introduces a second, competing source of gravity, one far more powerful than Earth's own gravitational field. Because gravity operates across space as a gradient, the side of Earth facing the black hole experiences a significantly stronger pull than the side facing away. This difference in pull across a given distance is the essence of a tidal force, and because gas is fluid, light, and unbound by structural bonds, the atmosphere responds to these tidal forces long before the solid iron core or tectonic plates feel the strain. The tidal bulge of the sky. As the distance between Earth and the rogue black hole shrinks, the atmosphere begins to deform into an exaggerated, egg-shaped envelope, a prolate sphere aligned directly with the black hole's trajectory. On the side of Earth facing the approaching Titan, the black hole's pull acts in direct opposition to Earth's gravity. The net gravitational force holding the upper air down begins to weaken. The air does not simply stay in place. It lifts outward, expanding into space like a towering cosmic mountain of transparent gas. Simultaneously, on the opposite side of Earth, a secondary atmospheric bulge forms, created because Earth itself is being pulled toward the black hole slightly faster than the distant atmosphere behind it. This phenomenon creates a colossal atmospheric tide. But unlike ocean tides, which rise and fall by a few meters along coastlines, the atmospheric tide stretches hundreds of kilometers out into the space void. As the upper layers of the thermosphere are pulled outward, they pass beyond a critical boundary known in celestial mechanics as the Roche lobe. The Roche lobe defines the spatial region around an astronomical body within which its own gravity dominates over the tidal pull of a nearby massive object. The moment Earth's expanded upper atmosphere spills over the edge of its Roche lobe, those gas molecules are no longer bound to Earth. They are captured by the black hole's immense gravitational slope. A vast, glowing stream of atmospheric gas begins to peel away from Earth, forming a thin, luminous bridge of stripped air drifting through space toward the approaching shadow. Earth is literally bleeding its sky into the cosmic void. Disruption of the geodynamo and the shielding collapse. The loss of atmospheric gas is accelerated by another, even more catastrophic effect occurring deep within Earth: the collapse of our planetary magnetic shield. Earth's atmosphere is preserved not only by gravity, but also by the magnetosphere, a giant magnetic bubble generated by the motion of molten iron and nickel churning in Earth's liquid outer core. This internal geodynamo acts as an invisible shield, deflecting the relentless solar wind, a stream of energetic charged particles blowing outward from the sun at hundreds of kilometers per second. Without the magnetosphere, the solar wind would gradually strike air molecules, stripping them away into deep space over millions of years. As the rogue black hole draws near, its differential gravitational force pulls not just on the surface ocean and sky, but also on Earth's heavy, molten iron core. The liquid interior experiences extreme internal tidal friction and gravitational torques. The smooth, convective rotation of the outer core is disrupted. As the flow of molten metal becomes turbulent and chaotic, the geodynamo begins to falter. Earth's magnetic field lines twist, weaken, and snap. The planetary magnetic shield breaks down. With the magnetosphere severely weakened, the full force of the solar wind hits Earth's elevated, tidally stretched upper atmosphere without resistance. Highly energetic solar protons and alpha particles crash into the exposed nitrogen and oxygen atoms in the outer sky, knocking them out of Earth's gravitational embrace through a process known as atmospheric sputtering. The planet is now caught in a dual assault. From above, the black hole's gravity siphons air off in sweeping tidal streams. From the side, solar radiation strips away the unshielded atmosphere at an unprecedented rate. The barometric drop in thermal chaos. As tens of billions of tons of air molecules stream out into space every minute, the total mass of the atmosphere drops rapidly. On the surface, this loss translates into a continuous, terrifying drop in barometric pressure. Under normal atmospheric pressure at sea level, water boils at 100 degrees Celsius. Atmospheric pressure acts like an invisible weight pressing down on the surface of liquids, keeping their molecules packed together in liquid form. But as the atmospheric mass thinned out into space, surface pressure plunges across the globe. As the barometric pressure drops toward a fraction of its normal state, the boiling point of water drops along with it. In warm equatorial oceans and shallow lakes, the water near the surface begins to boil spontaneously at room temperature. Vast clouds of vapor rise into the thinning sky, creating massive, unstable weather systems before evaporating completely into the upper atmospheric currents being pulled away by the black hole. Simultaneously, the loss of atmospheric mass destroys Earth's greenhouse effect. The atmosphere normally acts like a cozy thermal blanket, absorbing ground heat and keeping night temperatures mild. As the blanket thins, heat escapes instantly into space the moment the sun sets. The planet plunges into extreme thermal contrasts, blistering, unfiltered radiation scorching the surface during the day, followed by an immediate, bone-chilling freeze at night as heat radiates away into the clear, empty vacuum. The transformation of color and the growth of silence. To a human observer standing on the surface during these declining hours, the changes in the sky are both visual and acoustic. The brilliant blue color of our daylight sky is caused by Rayleigh scattering, a process where tiny nitrogen and oxygen molecules scatter shorter blue wavelengths of sunlight in every direction. But as the air thins to a whisper, there are fewer and fewer molecules left to scatter the light. The daytime sky undergoes a magnificent and surreal transformation. The bright blue hue begins to deepen into a dark, saturated indigo. Over the course of hours, the indigo fades into a deep, velvety violet. Eventually, even while the sun is shining brightly overhead, the sky turns jet black. Stars and constellations become clearly visible during the day, standing bright against a dark backdrop alongside a pale, distorted sun. The blue sky that defined Earth for eons has vanished, replaced by the stark, raw reality of deep space. Along with the change in color comes a profound, unsettling silence. Sound is a mechanical wave. It requires a physical medium, such as air molecules, to vibrate and travel from one point to another. As atmospheric density drops toward a near-vacuum state, the medium disappears. The sound of wind howling across mountains fades into a quiet rustle, then into absolute stillness. Loud ocean waves crash against rocky shores without making a sound. Thunderstorms flash across the dark horizon in total silence. The ambient noise of the natural world dies away, leaving behind a silence so absolute that it feels heavy. Space itself has descended to the surface. The final breath. In the final stages of atmospheric collapse, Earth stands stripped of its protection. The sky is no longer a shield, but an open window into the void. The remaining trace gases linger in isolated pockets near deep ocean basins and low-lying valleys, pulled thin by the immense gravitational forces shaping the horizon. The upper atmosphere has completely detached, forming a faint, glowing ribbon of ionized gas that arcs across space toward the black hole's dark photon sphere, a trailing remnant of the world that was. Earth has been transformed from a vibrant, blue world into a silent, pristine sphere of exposed rock and frozen oceans, floating naked in the cosmic dark under the shadow of the phantom wanderer. In the next chapter, we descend from the empty sky to the solid crust, exploring the catastrophic mechanical forces that arise when tidal gravity reaches the surface, the spaghettification and tearing of Earth's tectonic plates. With the atmosphere stripped into deep space and the oceans evaporated or blown out into the cosmic void, Earth floats as a bare sphere of rock and metal. To a distant observer, the planet appears preserved in an eerie, frozen state, its ocean basins dry, its continents exposed, and its surface exposed directly to the harshness of space. But this quiet period is fleeting. The gravitational forces acting on the planet are no longer just altering fluids or light. They are preparing to tear the solid planet apart. Every mountain range, tectonic plate, and grain of sand on Earth is held together by two fundamental forces: the mutual gravitational attraction of the planet's mass, and the electromagnetic forces holding atoms and crystalline structures together in solid rock. For over 4 billion years, these structural bonds were more than strong enough to resist any external pull. But as the 10 solar mass rogue black hole continues its approach, it subjects the planet to gravitational gradients that completely overpower the structural strength of solid matter. The tensile stress of space. To understand how a black hole breaks a solid planet, one must examine the difference in gravitational acceleration felt across the body of Earth. Gravity weakens with distance. Therefore, the side of Earth closest to the black hole is pulled with significantly greater force than the center of the planet, and the center is pulled far harder than the far side. This difference creates a severe stretching force along the line of sight connecting Earth and the black hole. At the same time, because all gravitational field lines converge toward the central mass of the black hole, the sides of Earth perpendicular to this alignment are squeezed inward. This dual action, stretching along the line of approach and squeezing along the sides, is the foundational physics of spaghettification. When applied to a fluid, it stretches the gas into an elongated envelope. But when applied to a rigid planetary sphere made of granite, basalt, and iron, it creates immense internal tensile stress. The planet is pulled in opposite directions from the inside out. The awakening of the fault lines. Long before the planet physically elongates into a teardrop shape, the internal mechanical stress concentrates along the weakest structural lines in Earth's crust, the tectonic fault lines. Earth's crust is not a single solid shell. It is fragmented into massive tectonic plates that drift on top of the ductile, semi-fluid mantle beneath. Under normal conditions, these plates move at speeds of millimeters per year, driven by slow convection currents deep within the interior. Sudden releases of friction between these sliding plates cause conventional earthquakes. As the black hole's tidal gradient intensifies, the stress applied to these plate boundaries increases by millions of times in a matter of hours. The rigid continents are forced to deform. Deep beneath the crust, locked fault lines like the San Andreas Fault, the Mid-Atlantic Ridge, and the Ring of Fire snap simultaneously across thousands of kilometers. Massive megathrust earthquakes, scaling far beyond anything recorded in human history, ripple continuously across the globe. These are not brief seismic events that last for seconds or minutes. They are continuous planetary vibrations that shatter the crystalline structure of the crust. Continental rupture and mantle unroofing. As the stretching force exceeds the ultimate tensile strength of basaltic rock, the tectonic plates begin to pull apart physically. Colossal rifts, miles wide and hundreds of miles deep, tear across the continental shields. In regions where the crust is thin, such as the ocean floors and rift valleys, the crust splits open entirely, exposing the glowing, semi-molten mantle beneath. Without the crushing weight of the atmosphere and the missing ocean water pressing down on the seabed, the pressure inside the mantle drops rapidly. This sudden decompression causes the solid rock of the mantle to undergo decompression melting. Millions of cubic kilometers of mantle rock instantaneously melt into liquid magma. Fountains of glowing orange lava blast through the tearing crust, creating continuous curtains of fire that stretch across entire continental landmasses. The surface of Earth transforms from a dry, shattered rock into a glowing, volcanic nightmare, a planet glowing in the dark as its molten interior spills out into space. Crossing the Roche limit for solids. As Earth is drawn closer to the phantom wanderer, it reaches a critical gravitational boundary known as the fluid and rigid Roche limits. The Roche limit is the precise distance at which a celestial body's internal self-gravity, the gravitational pull that keeps it spherical, can no longer hold it together against the tidal forces of a larger body. Beyond this boundary, the tidal pull exceeds the planet's own gravity, and the body can no longer maintain a stable, bound shape. For a planet composed of rock and iron, there are two stages to crossing this threshold. The outer Roche boundary, the point where unattached surface material, boulders, loose mountain soil, shattered rock, and lava flows, loses its weight entirely. On the side of Earth facing the black hole, gravity becomes negative relative to the surface. Rocks and glowing magma streams detach from the ground and fall upward into space, flowing into the dark void. The inner rigid Roch limit, the point where even the atomic structural strength of solid iron and granite cannot resist the differential pull. Here, the planet loses its structural integrity completely. Once Earth passes the inner Roch limit, the planet does not simply crack, it disintegrates. The process of spaghettification. Now, the classic relativistic phenomenon of spaghettification takes full effect. Earth is no longer acting as a solid planetary body. It is transformed into a stream of unbound, freely falling material. The spherical shape of Earth collapses. The planet stretches out into an elongated, glowing filament thousands of kilometers long, while simultaneously squeezing down into a narrow tube of shattered debris. The core of the planet, a dense, superheated sphere of solid iron and nickel surrounded by a molten outer core, is drawn out like taffy. The intense gravitational differential pulls the leading edge of the core toward the black hole at a far higher acceleration than the trailing edge. The iron core stretches into a long, radiant thread of white-hot liquid metal. Following the core, the shattered fragments of the mantle and crust form a vast stream of glowing rock, mineral dust, and volcanic debris. What was once a vibrant world with continents, cities, mountain ranges, and history is reduced to a thin, luminous stream of matter flowing quietly along the curved lines of warped space. The accretion stream. As this elongated stream of planetary matter approaches the black hole's photon sphere, it does not strike a solid surface. There is no hard floor to impact, no flash of collision, and no sound. Instead, the stream of shattered Earth matter enters an orbit around the central shadow, forming a temporary, ultra-hot ring of matter known as an accretion disk. As the matter circles the black hole at speeds approaching a significant fraction of the speed of light, internal friction between colliding rocks, iron dust, and gas heats the debris stream to millions of degrees. The destroyed remnant of Earth glows brightly in extreme ultraviolet and X-ray radiation, illuminating the black hole's dark photon sphere one last time. Chunk by chunk, atom by atom, the glowing stream spirals inward past the photon sphere, crossing the invisible boundary of the event horizon. Inside the horizon, the matter that once formed Earth is drawn down to the central singularity, its mass added forever to the total gravitational mass of the silent, wandering black hole. The planet has vanished from the observable universe, leaving behind only space, curved geometry, and complete darkness. Beyond the threshold of shattered rock, ionized atmospheric gases, and distorted starlight lies the absolute boundary of space, the event horizon. It is not a solid surface, nor a glowing wall of fire, nor a physical obstacle. It is a mathematical surface, a point of no return where the escape velocity of space itself matches and exceeds the speed of light. As the stream of matter that once constituted Earth cascades inward, it approaches this invisible boundary. Up until this precise moment, every event in the history of our world was connected to the rest of the universe by light, energy, and cause and effect. But crossing the horizon represents a final, irreversible break in the causal structure of reality. The boundary of no return. To an observer watching from far away, nothing ever truly appears to cross the event horizon. Because time stretches infinitely from an external frame of reference, the falling remnants of Earth seem to slow down as they approach the shadow. Their light grows dim, redder, and fainter, freezing on the perimeter like a ghostly frame frozen in time. Yet for the matter itself falling inward, there is no pause. The crossing of the event horizon happens in a continuous, uninterrupted sweep. If an astronaut were drifting inside this stream of matter, looking back as they crossed the line, They would not feel a sudden impact or bump in space. The local geometry of spacetime feels smooth at the boundary itself, but looking out toward the external universe, the entire history of the cosmos would appear compressed into a bright, shrinking circle of light directly above. The outer universe speeds up, running its course in accelerated motion, while below lies only an absolute, unbroken void. The inversion of space and time. Once inside the event horizon, the fundamental coordinate system of the universe undergoes a radical, mind-bending inversion. In normal space outside a black hole, you are free to move in any direction, left, right, up, or down, but you are forced to move forward in time. Time is a one-way path from the past into the future. You cannot stop moving toward tomorrow any more than you can step out of the current second. Inside the event horizon, the intense curvature of spacetime causes the spatial and temporal coordinates to swap roles. The radial direction leading toward the central singularity is no longer a direction in space. It becomes a direction in time. The center of the black hole is no longer a place you can choose to travel toward or avoid. It becomes a temporal moment, your inevitable future. Trying to escape or fire rocket engines to move away from the center inside an event horizon is as impossible as trying to travel backward into yesterday. Every path through space, no matter how hard you push or turn, leads directly toward the central point. Space itself is collapsing inward faster than light, carrying all matter, energy, and light toward a singular temporal destination. The approach to the singularity. As the remnant stream of Earth moves through the interior of the black hole, the gravitational gradient rises to infinite proportions. In classical general relativity, at the exact center of this distortion sits the singularity, a point where mass is compressed down into zero volume, resulting in infinite density and infinite curvature of spacetime. Here, the smooth fabric of space is torn completely, and the known equations of physics cease to function. As matter approaches this central point, tidal forces increase without bound. At distances fractions of a millimeter from the singularity, the gravitational difference across even the size of an atom becomes so vast that atomic nuclei are stretched apart into individual protons and neutrons. Further down, the subatomic particles themselves lose their structural identity, dissolving back into fundamental quantum fields. The quantum limits of reality. Before reaching true mathematical infinity, physics encounters the Planck scale, the fundamental threshold where general relativity must yield to quantum mechanics. At this microscopic scale, space is no longer a smooth, continuous fabric. It breaks down into a turbulent, chaotic foam of quantum fluctuations where space, time, cause, and effect lose all distinct meaning. The mass of Earth, its iron core, its silicate mantle, its ancient memory of water and life, is stripped of all local physical attributes. According to the fundamental laws of black hole mechanics, a black hole possesses only three observable properties: mass, electric charge, and angular momentum. As Earth's matter merges into the central singularity, its vast complexity is reduced entirely to these three fundamental quantities. Its total mass is added quietly to the total mass of the black hole, slightly expanding the radius of the event horizon for eternity. The quiet aftermath. The phantom wanderer continues its lonely journey through the Milky Way galaxy. It leaves behind an empty orbit around the sun, a blank space in the solar system where a vibrant, blue-green world once looped for 4.5 billion years. The black hole carries no trace of the cities that stood on Earth's crust, the oceans that swept its basins, or the atmosphere that once blue-shifted the daylight. All of it has been integrated into the silent, eternal geometry of the singularity. The universe continues its grand, slow evolution. Stars are born in distant nebulae, galaxies drift apart in the expanding dark, and cosmic time marches forward. And somewhere in the interstellar quiet, the invisible Titan drifts on, carrying the mass of a forgotten world locked forever behind its horizon. Throughout our journey, we have examined the arrival of a stellar mass black hole, an object weighing roughly 10 times the mass of our Sun, concentrated into a sphere the size of a city. But black holes in our universe are not built to a single scale. They span an extraordinary spectrum of mass, ranging from microscopic primordial remnants formed in the first fractions of a second after the Big Bang to supermassive monsters anchored at the hearts of distant galaxies, containing billions of suns. If Earth were to encounter a black hole tomorrow, its ultimate fate would depend entirely on a single fundamental variable: mass. Mass dictates not only the physical size of the event horizon, but also the nature of the gravitational forces acting on matter. Counterintuitively, in the bizarre physics of general relativity, smaller black holes are often far more violent up close, while the largest giants in the cosmos can swallow an entire world in complete silence. The paradox of tidal strength. To understand why size changes everything, one must look closely at the paradox of tidal forces. Tidal forces arise from the difference in gravitational pull across a given distance. The steeper the change in gravity over a short distance, the stronger the stretching and squeezing forces become. In a stellar mass or microscopic black hole, the event horizon sits extremely close to the central singularity. Because the boundary is so small, the gravitational field drops off at a blindingly sharp rate over just a few meters. If a human or a planet approaches the event horizon of a small black hole, the difference in pull between the front edge and the back edge is staggering. The object is violently stretched into a thin strand long before it ever touches the boundary itself. However, as a black hole grows in mass, its event horizon expands proportionally. A supermassive black hole containing several billion solar masses possesses an event horizon spanning billions of kilometers, a boundary far larger than our entire solar system. Because the radius of the event horizon is so immense, the gradient of gravity at that boundary becomes remarkably flat. The change in gravitational force from one side of Earth to the other near the horizon of a supermassive black hole is gentler than the gravitational pull you feel standing on Earth's surface today. This leads to one of the most astonishing realizations in theoretical astrophysics. If Earth were drawn toward a supermassive black hole, it would cross the event horizon completely intact, without being torn apart, without earthquakes, and without spaghettification. Earth would slide past the point of no return while floating in pristine, unbroken quiet. Scenario A: the microscopic bullet. At the opposite extreme of the cosmic scale sit primordial black holes, hypothetical objects formed during the high-density environment of the early universe. A micro-black hole might possess the mass of a giant asteroid or a large mountain range, but squeezed down into a physical size smaller than a single atom. It radiates no light, casts virtually no shadow to the naked eye, and drifts through space like an invisible, infinitely sharp needle. What happens if a micro-black hole strikes Earth tomorrow? Unlike a stellar mass black hole, a microscopic black hole does not possess enough total mass to pull Earth out of its orbit around the Sun or strip the atmosphere from afar. Its gravitational influence is almost unnoticeable until it directly touches the planet. As it hits Earth at interstellar speeds, moving at hundreds of kilometers per second, it does not crash or explode like a conventional meteorite. It pierces the upper atmosphere without sound, passing straight through solid ground, continental crust, oceans, and mantle as if the planet were made of soft foam. As it passes through Earth's interior, it leaves behind a microscopic tunnel of superheated matter. Matter immediately surrounding its path is drawn inward by extreme localized gravity, creating a narrow accretion tube that glows at millions of degrees. The extreme density spike along its trajectory generates powerful seismic shockwaves, a deep, planetary ringing that echoes through the mantle. If the micro-black hole is moving fast enough, it simply passes straight through the planet, exiting out the opposite side of Earth and flying back into the void of space, leaving behind a narrow, cooling shaft of glassified rock through the core. Earth survives, shaken but physically intact. The parasite core scenario. However, if the micro-black hole enters the solar system at a slower relative velocity, a far more insidious scenario unfolds. Earth's gravity captures the micro-wanderer. As the small black hole passes through the planet, friction and gravitational drag slow its speed down below Earth's escape velocity. Unable to break free, the black hole falls back toward the center of the planet, passing back and forth through the core like a pendulum inside a hollow sphere. With every pass through the interior, it loses kinetic energy, until it eventually comes to rest at the absolute center of Earth's iron core. Now the black hole becomes a gravitational parasite. Sitting quietly at the center of our world, it slowly feeds on the high-density molten iron around it. At first, its appetite is minuscule, consuming only tiny amounts of matter per day. But as it feeds, its mass grows, and as its mass grows, its gravitational reach expands exponentially. Over months, years, or decades, the core is consumed from the inside out. As the center loses structural support, Earth experiences continuous global seismic collapses. The planet slowly shrinks inward, its crust buckling into massive fault lines as the hollowed interior gives way to the growing monster feeding in the dark. Eventually, the parasite consumes the mantle and crust from within, reducing Earth to a silent, stellar-sized black hole floating where our world once revolved. Scenario B: the cosmic ocean of supermassive black holes. Now turn your gaze to the opposite end of the spectrum. An encounter with a supermassive black hole, such as the one residing at the center of the galaxy M87, weighing over 6 billion times the mass of our Sun. If such a titan were to drift into our region of space, the scale of destruction shifts from localized mechanics to total cosmic engulfment. As the supermassive black hole approaches, its gravitational sphere of influence encompasses the entire solar system simultaneously. The Sun, Earth, Mars, Jupiter, and the outer gas giants are caught within the same smooth, overwhelming gravitational incline. There is no violent differential tug pulling Earth away from the Sun. Instead, the entire solar system is drawn inward together, maintaining its relative planetary positions as it falls into the vast gravitational ocean. To an observer on Earth, the sky would not feature a small, violent shadow tearing at the land. Instead, a black horizon would rise up to swallow the entire sky. The darkness would expand until it filled half of reality, framed by a brilliant, shimmering ring of starlight where the rest of the universe's light was bent around the colossal boundary. Because the tidal forces at the event horizon of a 6 billion solar mass black hole are virtually zero, Earth crosses the threshold without a single tremor. The atmosphere remains still. The oceans remain flat. The sun shines calmly in the sky. Yet the moment Earth crosses that invisible line, the universe outside vanishes forever. The future of the planet is locked toward the distant central singularity billions of kilometers ahead. It is a slow, peaceful execution, a world drifting in silence toward an inevitable temporal end, blissfully unaware of the moment it stepped past the edge of existence. Mass as the cosmic director. Whether by microscopic bullet, stellar mass destruction, or supermassive engulfment, the mass of the black hole dictates the story of the end. Micro-black holes act like scalpels, cutting through solid matter with hyperlocalized intensity. Stellar mass black holes act like cosmic engines of chaos, tearing planets apart through violent tidal stretching and atmospheric stripping. And supermassive black holes act like vast, silent oceans, swallowing entire star systems whole without leaving a single ripple on the surface. In the next chapter, we look beyond the physical death of the planet to explore the deepest mystery of theoretical physics, the holographic principle, Hawking radiation, and whether the quantum memory of Earth can ever truly be destroyed. When a world is swallowed by a black hole, common sense suggests that it is erased. The oceans, the mountain ranges, the cities, the historical records, and every atom that once formed living beings are drawn into a singularity and crushed out of physical reality. To the classical eye, the destruction appears absolute. Yet deep within the foundations of modern theoretical physics sits a profound contradiction, one that has puzzled cosmologists for over half a century. In the realm of quantum mechanics, there is a sacred law known as unitarity. Unitarity dictates that information in the universe can never be truly destroyed. The quantum states of particles, their spins, positions, charges, and relational histories, can be scrambled, heated, or scattered across light years, but the fundamental code of reality must always be preserved. If you burn a physical book, the pages turn to ash and smoke. Reassembling that book with human hands is impossible. But in theory, if you were to collect every single photon of light emitted by the fire, every particle of smoke, and every speck of ash, quantum mechanics asserts that you could mathematically reverse the process and reconstruct every word written on those pages. The information was never destroyed. It was merely scrambled into chaos. This brings us to the ultimate cosmic puzzle. If Earth falls into a black hole, what happens to its quantum information? Is the code of our planet erased from existence, or is it woven into the subtle geometry of the cosmos forever? The black hole information paradox. The conflict began in the 1970s with the work of physicist Stephen Hawking. Combining quantum field theory with general relativity, Hawking demonstrated that black holes are not entirely black. Near the event horizon, quantum vacuum fluctuations constantly produce pairs of virtual particles, a particle and its antiparticle companion. Normally, these virtual particles appear together, annihilate each other instantly, and vanish back into the quantum foam. But at the edge of an event horizon, a different process unfolds. One particle falls across the boundary into the black hole, while the other particle escapes into deep space. To maintain energy conservation, the particle that falls inward carries negative energy, slightly reducing the total mass of the black hole. The escaping particle becomes real, radiating outward as thermal energy. This thermal glow is known as Hawking radiation. Over incomprehensibly vast timescales, this process causes the black hole to slowly lose mass, shrink, and eventually evaporate into nothingness. But Hawking's early calculations suggested something disturbing. The radiation escaping from a black hole appears purely thermal and featureless. It carries no memory of what fell inside. If a black hole formed from a collapsing star swallows a planet, feeds for billions of years, and then completely evaporates into featureless thermal radiation, where did the information go? If the information inside is destroyed when the singularity vanishes, the fundamental law of quantum mechanics breaks down. This contradiction is known as the black hole information paradox. The holographic principle, space as an illusion. To solve this paradox, physicists Gerard T. Hooft and Leonard Susskind introduced one of the most radical concepts in modern science, the holographic principle. The holographic principle suggests that our intuitive perception of three-dimensional space is an illusion. It proposes that all the physical information contained within a three-dimensional volume of space can be fully encoded onto a two-dimensional boundary surrounding that region. Much like how a two-dimensional credit card hologram projects a three-dimensional image when light strikes its surface. Applied to a black hole, the implications are staggering. As the matter that once formed Earth approaches the event horizon, it does not simply drop into an empty, silent pit. From the perspective of quantum physics, as particles touch the boundary of the horizon, their three-dimensional quantum states are stretched and printed onto the two-dimensional surface area of the event horizon itself. Every atom of Earth's core, every molecule of its ancient atmosphere, and every photon that ever reflected off its oceans is encoded into microscopic, Planck-scale quantum fluctuations ripple across the event horizon's surface. The black hole does not swallow the information into a dark void. It stores it like an immense, ultra-dense quantum hard drive. The surface area of memory. In classical physics, the storage capacity of a physical container scales with its volume. A room twice as wide, deep, and high can hold 8 times as much physical material. But black holes do not obey the laws of volume, they obey the laws of area. The total amount of entropy, or information storage capacity, that a black hole can possess is directly proportional to the surface area of its event horizon, measured in fundamental units called Planck areas. A Planck area is impossibly small, measuring a fraction of a millimeter across. Because these bits of information are packed together at the absolute physical limit of space, an event horizon can store an unbelievable density of quantum data. When Earth is drawn toward the shadow, its three-dimensional structure is flattened across the event horizon's surface. The planet's entire physical history is converted into a complex, scrambled pattern of quantum ripples vibrating at the speed of light along the perimeter of the horizon. Black hole complementarity, two realities at once. This leads to a fascinating question. What does an observer actually experience? If information stays on the surface while simultaneously falling inside, which reality is real? Leonard Susskind proposed the concept of black hole complementarity. According to this principle, both realities are true, but no single observer can ever witness both at the same time. An observer watching from a distance outside the black hole sees Earth approach the horizon, flatten out, and become encoded onto the boundary. To the outside observer, Earth never actually enters the interior. Its quantum code remains anchored to the surface, slowly being imprinted onto the subtle, chaotic fluctuations of Hawking radiation escaping back into the universe over trillions of years. Simultaneously, an observer falling with Earth experiences a completely smooth transition past the horizon, moving toward the central singularity as described by general relativity. Because no signal can ever cross back out from behind the event horizon to communicate with the outside observer, the two accounts can never be compared. Quantum mechanics is preserved for the outside world, while general relativity remains intact for the interior world. The two descriptions complement each other like two sides of a single coin. The cosmic legacy. In this atmospheric light, the death of Earth takes on a profoundly poetic meaning. Our world is not erased. The physical matter, the iron, the silicates, the carbon, and the water, may be crushed at the singularity or scattered into thermal radiation over trillions of years. But the fundamental quantum pattern that made Earth unique is never lost. Every mountain that ever rose, every ocean wave that ever broke against a shoreline, every creature that ever looked up at the night sky, and every thought that ever crossed a human mind leaves behind an indelible, microscopic footprint printed onto the boundary of space itself. Long after the sun has gone cold and the solar system has faded into cosmic memory, the code of Earth endures. It exists as a microscopic pattern etched onto the surface of a silent wanderer, a quantum hologram floating through the deep, timeless void of the universe. In the final chapter, we step past the end of physical matter to explore the ultimate aftermath, the quiet void after creation, and what it means for a universe to drift in eternal cosmic silence. When a world is swallowed by a black hole, common sense suggests that it is erased. The oceans, the mountain ranges, the cities, the historical records, and every atom that once formed living beings are drawn into a singularity and crushed out of physical reality. To the classical eye, the destruction appears absolute. Yet deep within the foundations of modern theoretical physics sits a profound contradiction, one that has puzzled cosmologists for over half a century. In the realm of quantum mechanics, there is a sacred law known as unitarity. Unitarity dictates that information in the universe can never be truly destroyed. The quantum states of particles, their spins, positions, charges, and relational histories, can be scrambled, heated, or scattered across light years, but the fundamental code of reality must always be preserved. If you burn a physical book, the pages turn to ash and smoke. Reassembling that book with human hands is impossible. But in theory, if you were to collect every single photon of light emitted by the fire, every particle of smoke, and every speck of ash, quantum mechanics asserts that you could mathematically reverse the process and reconstruct every word written on those pages. The information was never destroyed. It was merely scrambled into chaos. This brings us to the ultimate cosmic puzzle. If Earth falls into a black hole, what happens to its quantum information? Is the code of our planet erased from existence, or is it woven into the subtle geometry of the cosmos forever? The black hole information paradox. The conflict began in the 1970s with the work of physicist Stephen Hawking. Combining quantum field theory with general relativity, Hawking demonstrated that black holes are not entirely black. Near the event horizon, quantum vacuum fluctuations constantly produce pairs of virtual particles, a particle and its antiparticle companion. Normally, these virtual particles appear together, annihilate each other instantly, and vanish back into the quantum foam. But at the edge of an event horizon, a different process unfolds. One particle falls across the boundary into the black hole, while the other particle escapes into deep space. To maintain energy conservation, the particle that falls inward carries negative energy, slightly reducing the total mass of the black hole. The escaping particle becomes real, radiating outward as thermal energy. This thermal glow is known as Hawking radiation. Over incomprehensibly vast timescales, this process causes the black hole to slowly lose mass, shrink, and eventually evaporate into nothingness. But Hawking's early calculations suggested something disturbing. The radiation escaping from a black hole appears purely thermal and featureless. It carries no memory of what fell inside. If a black hole formed from a collapsing star swallows a planet, feeds for billions of years, and then completely evaporates into featureless thermal radiation, where did the information go? If the information inside is destroyed when the singularity vanishes, the fundamental law of quantum mechanics breaks down. This contradiction is known as the black hole information paradox. The holographic principle, space as an illusion. To solve this paradox, physicists Gerard T. Hooft and Leonard Susskind introduced one of the most radical concepts in modern science, the holographic principle. The holographic principle suggests that our intuitive perception of three-dimensional space is an illusion. It proposes that all the physical information contained within a three-dimensional volume of space can be fully encoded onto a two-dimensional boundary surrounding that region. Much like how a two-dimensional credit card hologram projects a three-dimensional image when light strikes its surface. Applied to a black hole, the implications are staggering. As the matter that once formed Earth approaches the event horizon, it does not simply drop into an empty, silent pit. From the perspective of quantum physics, as particles touch the boundary of the horizon, their three-dimensional quantum states are stretched and printed onto the two-dimensional surface area of the event horizon itself. Every atom of Earth's core, every molecule of its ancient atmosphere, and every photon that ever reflected off its oceans is encoded into microscopic, Planck-scale quantum fluctuations ripple across the event horizon's surface. The black hole does not swallow the information into a dark void. It stores it like an immense, ultra-dense quantum hard drive. The surface area of memory. In classical physics, the storage capacity of a physical container scales with its volume. A room twice as wide, deep, and high can hold 8 times as much physical material. But black holes do not obey the laws of volume, they obey the laws of area. The total amount of entropy, or information storage capacity, that a black hole can possess is directly proportional to the surface area of its event horizon, measured in fundamental units called Planck areas. A Planck area is impossibly small, measuring a fraction of a millimeter across. Because these bits of information are packed together at the absolute physical limit of space, an event horizon can store an unbelievable density of quantum data. When Earth is drawn toward the shadow, its three-dimensional structure is flattened across the event horizon's surface. The planet's entire physical history is converted into a complex, scrambled pattern of quantum ripples vibrating at the speed of light along the perimeter of the horizon. Black hole complementarity, two realities at once. This leads to a fascinating question. What does an observer actually experience? If information stays on the surface while simultaneously falling inside, which reality is real? Leonard Susskind proposed the concept of black hole complementarity. According to this principle, both realities are true, but no single observer can ever witness both at the same time. An observer watching from a distance outside the black hole sees Earth approach the horizon, flatten out, and become encoded onto the boundary. To the outside observer, Earth never actually enters the interior. Its quantum code remains anchored to the surface, slowly being imprinted onto the subtle, chaotic fluctuations of Hawking radiation escaping back into the universe over trillions of years. Simultaneously, an observer falling with Earth experiences a completely smooth transition past the horizon, moving toward the central singularity as described by general relativity. Because no signal can ever cross back out from behind the event horizon to communicate with the outside observer, the two accounts can never be compared. Quantum mechanics is preserved for the outside world, while general relativity remains intact for the interior world. The two descriptions complement each other like two sides of a single coin. The cosmic legacy. In this atmospheric light, the death of Earth takes on a profoundly poetic meaning. Our world is not erased. The physical matter, the iron, the silicates, the carbon, and the water, may be crushed at the singularity or scattered into thermal radiation over trillions of years, but the fundamental quantum pattern that made Earth unique is never lost. Every mountain that ever rose, every ocean wave that ever broke against a shoreline, every creature that ever looked up at the night sky, and every thought that ever crossed a human mind leaves behind an indelible, microscopic footprint printed onto the boundary of space itself. Long after the sun has gone cold and the solar system has faded into cosmic memory, the code of Earth endures. It exists as a microscopic pattern etched onto the surface of a silent wanderer, a quantum hologram floating through the deep, timeless void of the universe. In the final chapter, we step past the end of physical matter to explore the ultimate aftermath, the quiet void after creation, and what it means for a universe to drift in eternal cosmic silence. Where Earth once turned for 4.5 billion years, there is only an empty expanse of space. The sun continues to shine, casting its familiar golden light across the plane of the solar system. But that light no longer reflects off the azure oceans, white cloud tops, or rocky continents of our world. The orbit that once carried human history, civilization, and life sits blank. The gravitational disturbance of the passing rogue black hole has settled, leaving behind a slightly altered planetary arrangement, a solar family missing one of its inner terrestrial children. The black hole itself does not linger. It carries no memory of the destruction it wrought, nor does it pause to survey the empty space behind it. Moving at hundreds of kilometers per second, the silent wanderer glides out of the solar system, returning to the vast, cold interstellar void of the Milky Way galaxy. The quiet solar system in the immediate aftermath, the remaining planets adjust to the modified gravitational landscape. Without Earth's minor gravitational influence, the Moon, if any fragments survive the crossing, drifts as a rogue, frozen asteroid, or is drawn into a new, eccentric orbit around the Sun. Venus and Mars continue their ancient, silent loops through space, undisturbed by the absence of their neighbor. The Sun burns through its remaining reserves of hydrogen, completely indifferent to the fate of the third rock from its surface. 5 billion years from now, the Sun will expand into a red giant, swelling to engulf Mercury and Venus, shedding its outer layers into a glowing planetary nebula, and leaving behind a cooling white dwarf star. By the time the Sun reaches its stellar twilight, the event that erased Earth will be ancient history, lost in the deep silence of a changing galaxy. The journey of the wanderer, meanwhile, the rogue black hole carries Earth's total mass within its shadow across light years. As it drifts through the spiral arms of the Milky Way, it encounters interstellar gas clouds, cold dark matter, and stray photons from distant stars. Occasionally, it passes through a dense cloud of molecular hydrogen. The gas is drawn toward the event horizon, forming a temporary faint accretion ring that glows quietly in the dark before slipping past the point of no return. The mass of the black hole grows by microscopic fractions, a continuous collector of cosmic dust floating through the night. Over hundreds of millions of years, the Milky Way itself evolves. It collides and merges with the neighboring Andromeda galaxy, forming a massive, smooth elliptical galaxy known as Milkomeda. Stars are hurled into new orbits, binary systems break apart, and millions of new rogue black holes are ejected into the intergalactic abyss. The Wanderer moves beyond the boundaries of our original galaxy, drifting into the wide, quiet space between galactic clusters. The deep epics of space to understand the ultimate fate of the phantom titan carrying our world's mass, we must stretch our minds across timescales that dwarf all human understanding. Deep cosmic epics where stars go dark and galaxies fade into memory. The stellar era. The current cosmological era, where stars burn hydrogen, galaxies form new solar systems, and universe shines with light. This era will continue for roughly 100 trillion years, until the last red dwarf stars consume their fuel and quietly cool into black dwarfs. The degenerate era, a cold, dark cosmos where no new stars are born. The universe is populated entirely by dead stellar remnants, white dwarfs, neutron stars, brown dwarfs, and black holes. The sky is completely dark to the eye. The black hole era, an era stretching from $1040 to $10100 years into the future. By this time, even dead stars and white dwarfs have decayed or fallen into central black holes. The universe is dominated entirely by wandering black holes of all sizes, floating in an expanding, infinitely dark void. In this far-future epoch, our rogue black hole is no longer a rare phantom wandering among glowing stars. It is one of the primary inhabitants of a cold, silent cosmos. The final evaporation. Even black holes do not last forever. Through the slow, quantum process of Hawking radiation, the black hole slowly bleeds its mass back into the cosmos. Virtually imperceptible while the universe is young and warm, Hawking radiation becomes the dominant process in the cold expanse of the deep future. Particle by virtual particle, the black hole emits low-energy photons and neutrinos into the void. As it radiates energy, its total mass decreases. Because smaller black holes radiate energy faster than larger ones, the rate of evaporation accelerates as the black hole shrinks. Over an unimaginable span of roughly 1067 years, the 10 solar mass black hole that swallowed Earth shrinks down to the size of an atom, then to the Planck scale, before releasing its final remaining mass in a quiet, subtle burst of high-energy gamma rays. The mass that once formed Earth's iron core, its vast blue oceans, its granite mountains, and every living creature that ever walked its surface is finally returned to the universe. It is scattered across the expanding void as faint, highly redshifted photons of light, drifting forever through the infinite, peaceful dark. The cosmic equilibrium, the story of a rogue black hole destroying Earth tomorrow, is a reminder of our cosmic place. We live on a fragile blue island floating in a vast ocean governed by forces of incredible power and scale. The universe is neither cruel nor welcoming. It is a grand, continuous transformation of energy, mass, geometry, and light. Stars are born, planets take shape, life awakens to ponder the cosmos, and eventually matter returns to the space from which it came. When we turn off the lights and look out into the quiet night sky, we are not just looking at cold, distant stars. We are looking into the deep, timeless fabric of spacetime, a realm where everything is connected, where information endures, and where even the absolute quiet of the void carries the memory of creation.